Welcome back. In the part 1 video lecture, we discussed how a future 100% renewable energy system can look like. This model shows that on the generation side, the capacity of installed wind and solar electricity generation has to grow drastically. Can such supply chains from materials, manufacturing and installation of photovoltaic systems and wind turbines be realized? In this graph, I show the evolution of the effective power delivered by different electricity generation and storage technologies. After the invention of the Francis turbines in the late 19th century, the first hydroelectricity dams were constructed and taken in operation. Note that the vertical axis is on logarithmic scales. The hydroelectricity power has grown exponentially up to the 60s of the last century. Nuclear electrical power has been introduced in the 50s as shows an exponential growth up to the mid-80s, and then the installed power capacity quickly saturated. Saturation means that just as much operational capacity is installed as is dismantled. Every system has a technical or operational lifetime after which it needs to be replaced. Also plotted are the increasing capacity of solar and wind electrical power. Both technologies are still in an exponential phase. You can simply divide the evolution of installed capacity for technology in 3 phases. The last phase is the replacement market. Just as much capacity is installed as is being dismantled. The annual installations are determined by the total installed operational capacity divided by the lifetime of the system. The first phase is that both total installed capacity and annually added new installations is exponentially growing in time. The first phase ends at the point when the annual installed capacity does not grow anymore. The supply chain of materials, manufacturing components and installation and its annual market can never exceed the replacement market in the last phase to guarantee a financially sustainable supply chain. I understand that this is complex, but it basically means that maximum sustainable installation market, the transition from phase 1 to phase 2, is reached at a time span before the start of the replacement market in phase 3. And the funny thing is this is equal to the lifetime of a system. What does that mean? Let's take the projected global needed wind and solar power capacity following the earlier introduced global energy system based on 100% renewable energy in 2050. Wind supplies 80% and solar 69% of the electricity supply. This means solar and wind capacity needs to maintain an exponential growth of its annual market up to 2030 to establish the required annual market needed for the next 25 years after 2030 to realize 60% share in the total mix of power capacity in 2050. It means that in 5 years, an annual market of 3 terawatt for solar electricity should be realized. I also added some recent data of battery and electrolyzer power capacity installed worldwide. Although it's hard to find reliable data on global scale for both technologies, they seem to show an initial phase of exponential growth as well. Next to the model of the Energy Watch Group on global energy system based on 100% renewable energy, I have introduced in this videos and the previous videos, many other models exist and have been published in scientific literature by scientists, associations, governmental advisory committees, and industry itself. Do all these models result in the same final topology of the future energy system? The answer is no. I demonstrate that with the next graph out of a paper I have co-authored together with many experts around the world. The method we use here is the penetration of solar and wind energy to the energy system. With other words, what is the final share of solar and wind energy to the total energy mix? The penetration of solar is plotted on the horizontal axis and the penetration of wind is plotted on the vertical axis. As you clearly can see, the results of all models scatter broadly in the wind-solar penetration space. Why do all these models give so many different results? Many reasons can be given. The quality of the technical model that simulates the operation of the energy system, what is the time resolution, To what detail in the space are the components in the energy system worked out in the model? Another aspect is the assumption put in the model and the quality of the data being used. As you can see here, the integrated assessment models of the fifth assessment cycle of the IPCC resulted in a rather low penetration depth of solar energy. The reason being, outdated cost data for photovoltaics was used. Cost prices for 2050 were assumed that were even higher than the cost prices already realized in 2020. It's logic you will arrive at a low solar electricity penetration depth. In the sixth assessment cycle of the IPCC report, a lot of progress has been made in understanding the role of renewable electricity and its cost. In the IPCC's report on mitigation of climate change in 2022, this bar graph was published. The graph shows the potential contribution to net reduction in CO2 emissions by 2030 per technology. The length of the bar shows the amount of net reduced CO2 emissions expressed in equivalent CO2 emission per year. The colors along the bars represent the cost per additional reduction in the emission. The blue color represents that corresponding technology is cheaper than the reference based on a CO2 emitting fuel. The graph basically shows that wind and solar energy are the technologies that on short term can have the biggest contributions to replacing CO2 emitting energy technologies with renewable electricity. In addition, these technologies are for a large part, see the blue color, cheaper than the fossil fuel-based technologies. In summary, the maturity and cost price for solar and wind energy predicts a dominant role of these technologies in the future energy mix. And let's assume we would realize the around 8 gigatons of CO2 equivalent per year reduction by the deployment of solar and wind. We would in principle be able to follow the CO2 emission scenario that ends at a 1.5 degree global warming at the end of the century. Another way at looking at the energy transition we have seen so far is looking at the share of global electricity capacity addition per year per technology. So this is the new capacity of plants, installations to generate electricity added every year. Note it does not include the dismantlement of various technologies. I show here the data from 2008 up to 2023. The red and blue colors represent the coal and gas plants that convert fuels as gas and coal into electricity. It is clearly seen that these CO2 emitting technologies on global level are quickly phasing out. If we focus on the renewable electricity generation technologies like solar, wind and hydro, their share of added capacity was globally over 90% in 2023. The energy transition towards a renewable energy infrastructure has started. How do the various scenarios relate to the CO2 reduction scenarios? For that, I will use the World Energy Outlook report that are annually published by the International Energy Agency. This is the data from the Energy Outlook report from 2019. The red line represents the CO2 emissions if the current energy infrastructure would not change, a business as usual scenario. The blue line represents the International Energy Agency's stated policies scenarios, the STEPS policies, which is an World Energy Outlook scenario that projects the future energy system based on existing government policies and announced plans, providing a baseline of current trends, not aspirational goals, showing a trajectory leading to a significant global warming of around 2.5 degrees Celsius by the end of this century if these policies are fully implemented without further action. Next to the STEP scenario, the International Energy Agency introduced the Announced Pledges scenario. The Announced Pledges scenario is a model that gives a future where governments and industry meet all their stated climate and energy transition commitments, like the net zero targets and nationally determined contributions, fully and on time, even if specific policies to achieve them aren't yet into place. So commitments are not the existing policies and announced plans. The APS serves as a benchmark. It would correspond to a potential outcomes such as a 1.7 degrees Celsius warming by the end of this century, illustrating the significant different ambitions makes compared to just current policies, but is not a prediction, just an exploration of announced goals. In addition, the International Energy Agency introduced the net zero emissions. The net zero emissions by 2050 scenario is a detailed pathway for the global energy sector to achieve a net zero CO2 emission by 2050, consistent with limiting global warming to 1.5 degrees Celsius, requiring massive shifts like tripling renewables, doubling energy efficiency, eliminating fossil fuel investment, and widespread electrification by 2030, with developed nations leading the charge. These are how the scenario subtle changes in the 2022 report. In 2022, a lot of progress was made by announcing goals by the various governments. And here you see how the scenarios has subtle changed in the 2023 report and the 2024 scenario. Every year progress is made on existing government policies and announced plans. The forecasted emissions in 2050 for the STEPS model keeps dropping as indicated by the blue lines. Having said that, the net zero emission scenario, the lines are getting steeper and steeper, moving the 1.5 degrees Celsius target currently out of reach. In these two video lectures, we have discussed an example of how a 100% renewable energy future can look like. We also have discussed typical timescales of introducing new technologies for the energy transition and how our current existing policies, announced plans and announced ambitions for the energy transition relate to the various scenarios for CO2 emission reduction. I hope this week has been a helpful introduction into the general concepts of the energy system and how to understand the transition to renewable energy systems can be made. In the following weeks, my colleagues will dive into the more details of various aspects of the energy system, like the electrical power system, sustainable heating systems, industrial decarbonization, and energy markets and policies. Thanks for your attention and enjoy the rest of this course. I will see you back in the second Energy MOOC focus on technology. So, see you back in the next course.